Good day to you, Mr. Desmond. My name is Keshara Balasubramaniam and my group member is Darshan. So today I'll be talking about our project for computer architecture. Today we are delving into the program execution expressions with the example a plus b times c minus d. This expression is carefully chosen to illustrate key concepts in computation such as its transformation to postfix notation, the use of stack diagram, and its execution through various machine instruction sets. Let's first focus on the conversion to postfix notation. This step is crucial in enabling computers to process mathematical expressions efficiently without the need for parentheses. For our expression a plus b times c minus d, the postfix notation is ab plus cd minus times. Here's how we arrive at the result broken down step by step. First, solve the first part, which we will start with a plus b, which becomes ab plus in postfix notation. Second, we have to solve the second part, which is handle c minus d, which becomes cd minus. Lastly, we must combine and multiply, where we will multiply the result of the two sub-expression resulting in ab plus and cd minus x. Through this process, you can see how the hierarchy of operations is preserved and the notation becomes machine ready. In the next section, we'll explore how this postfix representation is visualized using stack diagrams and how it translates into machine instruction sets for execution. Now I will walk you through a step-by-step execution for an arithmetic expression using stack operations. The process involves pushing operands onto the stack and performing arithmetic operations in a last in first out LIFO manner. Let's break it down step by step. So now I'll be explaining you in step by step. Step 1, push A. We start by pushing operand A onto the stack. The stack now contains A. Step 2, push B. Next we push operand B onto the stack. Now the stack holds A and B. Step 3, perform A plus B. The top two elements on the stack, A and B, are popped. They are added together, which will be A plus B. The result is then pushed back onto the stack. The current stack state is A plus B. Step 4, push C. Operand C is pushed onto the stack. The stack state will be A plus B, C. Step 5, push D. Next, operand D is pushed onto the stack. Stack state A plus B, C, D. Step 6, perform C minus D. The top two elements on the stack, C and D, are popped. They are subtracted C minus D. The result is pushed back onto the stack. Stack state A plus B, C minus D. Step 7, perform multiplication. Finally, the two top elements on the stack, A plus B and C minus D, are popped. They are multiplied together, which will be A plus B times C minus D. The final result is then pushed back onto the stack. This completes our stack-based evaluation of the given arithmetic expression. The final result stored in the stack represents A plus B x C minus D. In conclusion, this method demonstrates how stacks efficiently handle arithmetic expressions following postfix notation. By systematically pushing operands and performing operands in the correct sequence, we can evaluate expressions accurately and efficiently. Now let's look at how this expressions A plus B times C minus D is executed step by step using machine instructions. Here's how the computation unfolds, simulating how a processor would handle it. Now I'll start with zero address machine instruction. Push A. The first step is to push the value of A onto the stack. This means A is now stored and ready for computation. Push B. Next, we push B onto the stack. Now the stack contains A and B ready for the addition operation. Third is add. The add instruction pops A and B from stack, performs the addition A plus B and pushes the result back onto the stack. The following will be push C. C is pushed onto the stack. Next will be push D. Similarly, D is pushed onto the stack. At this stage, the stack contains A plus B from the previous calculation as well as C and D. Next will be sub. The sub instruction pops C and D from the stack, computes the difference C minus D, and pushes the result onto the stack. Finally is multiplication. The mul instruction pops the two results A plus B and C minus D from the stack, multiplies them, and pushes the final result back onto the stack. This process showcases the efficiency of using a stack-based approach for computation, with each step working methodically to break down and solve the problem. Through this sequence, you can see how even a complex expression is decomposed into a series of simple machine-readable instructions, paving the way for execution in real time. Now, let's explore another method for executing the expression A plus B times C minus D. This time, we will use accumulator-based machine instructions, where an accumulator is a central register for temporary computation. Here's how the process works. Now, I'll be talking about one address machine instruction. Load A. First, we load the value of A into the accumulator. This is the starting point of our computation. Next is add B. We add B to the accumulator, efficiently performing A plus B. The accumulator now holds this result. Next will be store T1. We store the intermediate result A plus B into a temporary register T1 for future use. Load C. Now we load C into the accumulator. Next will be sub D. From the accumulator, when we subtract D, computing C minus D. The following will be store T2. This result C minus D is stored in another temporary register T2. Load T1. The process with the multiplication, we load the first result A plus B from T1 back into the accumulator. The following will be multiply T2. We then multiply the accumulator's value by the second result C minus D stored in T2. At this stage, the accumulator holds the final result. Finally, store E. We store the computed result into the register E, completing the operation. This method demonstrates how intermediate results are stored and retrieved for multi-step calculation, highlighting the role of temporary registers like T1 and T2. The sequence efficiently breaks down the task, making complex computations manageable. Through this approach, we see how machine instruction sets can leverage temporary storage and the accumulator to process mathematical expressions step by step, optimizing execution and accuracy. Let's examine another efficient method for executing the expressions A plus B times C minus D. This time we'll utilize a register-based machine instruction approach where registers act as high-speed storage to hold and manipulate intermediate values. Here's how the process works. Now I'll be talking about two address machine instructions. First, move A R1. First, we move the value of A into R1, which will act as a working register. Add B R1. Next, we add the value of B to R1, updating its contents to A plus B. At this stage, R1 contains the first part of our calculation. Move C R2. We then move the value of C into another register R2 to begin processing the second part of the expression. Next will be sub D R2. From R2, we subtract D, resulting in C minus D. Now R2 contains the second component of the calculation. The following will be the mul R2 R1, which is multiply R2 R1. The next step is to multiply the values in R2 and R1. This calculates the final result A plus B times C minus D. The result is stored in R1. Move R1 E. Finally, we move the computed result from R1 into E, where it is stored as the final output. This register-based approach is particularly efficient because it minimizes the need for accessing memory during computation. By keeping all intermediate results with the registers, the process ensures faster execution instruction. As you can see, each of these steps directly mirrors the arithmetic operations of the original expression, demonstrating the power of registers to handle and streamline complex computations efficiently. This method is widely used in modern computing systems for its speed and simplicity. Finally, let's examine a streamlined approach to executing the expression A plus B times C minus D using a modern, efficient, register-based instruction set. This method simplifies the process into just 3 instructions, which is 3 address machine instruction. First, add R1 A B. First, we calculate A plus B and store the result in R1, a register used for intermediate computations. Next is sub R2 C D. We compute C minus D and store the result in R2. Finally is multiply E R1 R2. We multiply the values in R1 and R2, which represents A plus B and C minus D respectively, and store the final result in E. This sequence of instruction highly efficient. It eliminates the need for temporary memory storage and leverages registers to handle intermediate results, resulting in faster and more straightforward computation. In just 3 concise steps, we've executed a multi-part mathematical expression showcasing the power and efficiency of modern instruction sets in computational process. That's all from me and my group. Thank you so much.